So we saw from the Desmos file an illustration of this definition of the limit. We said as we kept moving x closer to -1, we found out that y was moving closer to -2. So I'm going to write that down. As x moved closer to -1, y moved closer to -2, or sorry, +2. So that shows that there is a limit, that we are finding that we can keep f of x arbitrarily close to 2 by keeping x sufficiently close to -1. Okay, that's basically what we're saying here. It might be easier just to say that the limit is the number that y gets close to when x gets close to -1. So how do we do formal limit notation for this? You see the limit, L is the limit as x goes to -1 of f of x. So let's first of all substitute f of x in here. So we're saying the limit as x goes to -1 of the quantity 2 over x plus 2. Well, to evaluate a limit, the first thing you always try is to put this value for x into the function. So we say 2 over -1 plus 2, which is 2 over 1, which is 2. So this just tells me the limit of f of x at x equals -1 is 2. This is the boring limit, because we really didn't need to use a limit to figure out that when x gets close to -1, y gets close to 2, because that's just a point on the graph. -1, 2 is a point on the graph. We're going to look now, having talked about what happens when we move towards a point in both the x and y direction. Let's look at some more interesting ones now. So the next we're going to look at is the same function, but what if we try to find the limit of x, f of x as x approaches -2? So when we looked at Desmos on that, we realized there's an asymptote here at -2. And if we took a point, say right here, and tried to move it closer, x closer to -2, we found out that y just went off to -infinity. And when we took a point over here and tried to move it closer to -2, we found out that y just went off to +infinity. So we have a problem here. Now what happens when we actually look at this limit? Well, when we put -2 in the function, we get 2 divided by 0. We know from before that that means we have an undefined, or y is undefined when x equals 2. Sorry, -2. When x equals -2, you're going point, half point, half point. So we can say as x goes to -2, y goes to positive or negative infinity. Y is not getting closer to any particular number as x gets closer to 2. So no limit exists at x equals -2. Sorry, that's -2, not +2. I keep writing +2. So no limit exists at -2. We call this an infinite discontinuity. Infinite discontinuity. And this is where a vertical asymptote occurs on the graph. This big, large gash. As I said before, we're traveling along our graph, and all the, it looks just traveling along, all of a sudden big gash, travel along, big gash. That big gash is that infinite discontinuity. There is no putting that thing back together. But we have another type of discontinuity. And this is the kind of discontinuity we have when there's a hole in the graph. So if we put 2 in this function, we would get 4 minus 2 minus 2 over 2 minus 2, which is 0 over 0. This indicates a hole in the graph, and you remember from our previous unit that the hole would have to occur when x is 2. So when x is 2, that would be the hole on the graph. But this is a little different because it is called a removable discontinuity. This is different because as x gets closer and closer to 2, y is getting closer and closer to 3. The fact that it can't equal 3 doesn't matter for a limit. It just has to get close to it. So, write this down, as x gets close to 2, y gets close to 3. So there is a limit. So the limit of f of x at x equals 2 is 3. Now, how do you find that without actually looking at the graph, though? Pretty simply. What we do is we say, got this limit as x goes to 2 of x squared minus x minus 2 over x minus 2. Now we know since the denominator is 0 when x is 2, and we also got a 0 in the numerator when x is 2, that we have to have a common factor of x minus 2. I forgot something. I still need my limit terminology. Don't forget that. Limit as x goes to 2, because I haven't actually plugged 2 in yet, so I need to still have this here. So x, there should be an x minus 2 in both the numerator and the denominator because the numerator and the denominator are both made 0 when x equals 2. If we finish factoring the numerator, the other factor is x plus 1. Now we can remove the discontinuity. Okay, this is called a removable discontinuity because I can remove it. Continuity. Okay, so it can be removed. Now I'm just going to take the limit as x goes to 2 of x plus 1, and that's just 2 plus 1 equals 3. So when there's a hole in the graph on a rational function, I can always remove the discontinuity and find the limit. So the limit equals 3, and that means there is a hole at 2, 3. Okay. The next page is going to be more of a summary of all the things we've learned, so I'm going to go through that in a separate video.